All right, guys, I think it is time to get rolling. So my name is Andreas Bastian. This is Andy Harris, and I'll go ahead and let him kick things off here.
Cool. So I'm Andy Harris. I'm from the Advanced Consulting team. So I'm just going to give you a little overview of the Advanced Consulting team. So we are technical specialists. We all come from industry. And what our aim is to always work with industry in collaboration to basically develop innovative solutions. And we do so by producing high-performance products and trying to meet the big challenges that the industry has. And we're doing so by exploiting the leading edge of technology. By collaborating with industry, we're improving your knowledge, and we're also ensuring our software stays relevant. So here are some of the areas we work in. So we have adaptive manufacturing, robotics programming, additive manufacturing, build verification, inspection, composites design and manufacturing, and sheet metal nesting. We also do subtractive manufacturing. So in my team particularly, we work in the additive side. And as part of that, we do a lot of design. So we have topology optimization, lattice optimization, generative design. So we're going to learn a bit about both of those today. And we do build preparation, additive build simulation, and some material science and testing. So these are our main sort of areas that we work in. So we have lightweighting of structural parts, aesthetic designs, multifunctional parts, automotive components, aerospace, medical, plus other areas. And we also work on heat exchangers and tooling. Great, and
I hail from a different research wing of Autodesk over at Pier 9, which is a 27,000 square foot research facility that we have in downtown San Francisco. I'm a principal research scientist there based on our NetFab team, so looking primarily at how we can use additive technologies in a way that is both economical and practical. There's a lot of excitement around these technologies, and we're spending a lot of time looking at how we can use them very strategically. So at Pier 9, it's an interesting facility and one of several kind of digital fabrication workshops we have around the world. We have a bit of a focus on certainly digital fabrication, robotics. We do a lot of workflow research, and one of the more interesting things we have is a residency program to bring both individuals from industry in to work with our new generative design tools, to work on manufacturing, as well as to work on some very social impact challenges. One of the most unique things about the research that we do at Pier 9 is it's really focused on integrative and cross-disciplinary work. So we're looking at new ways of training robots, new ways of making robots build structures, new ways of embedding computers on the body via conductive textiles and embedded computers. So we're really looking at how can we combine existing technologies and how we can advance existing technologies with just little leaps in combinations. So today we're going to be talking about one of these combinations of new technologies and old technologies. We're going to be talking about metal casting, which is what the technology that is used to produce every part on the table. There's no 3D printed parts on this table. And afterwards, during Q&A, we'll pass some of these around so you can handle them, take a closer look. So Andy here is going to give you guys an overview of some of the generative design and lattice optimization capabilities that we're leveraging to really drive this manufacturing process. And I'll be talking a little bit more on the manufacturing side about how specifically two metal casting processes work and some of the design considerations for actually making parts for both investment casting, which is what was used to make this magnesium lattice seat frame over here on the right that Andy designed, as well as sand casting, which was used to make the LS 2 1/8 swing arm, which is down on the show floor, which you'll all be able to see later today, as well as a small prototype hack rod chassis up here. So with that, I'll hand back over to, I'm actually going to talk about why should we actually look at metal casting. It's a 5,000-year-old technology, and for kind of all intents and purposes is associated with a lot of kind of old, crusty, heavy industrial equipment, things like that. But in fact, we all flew here on airplanes with engines made out of investment cast parts. Most of the hot stage components of turbines are made out of investment cast parts. So it's actually a pretty interesting technology. And when we take a look at, kind of what's been driving a lot of the excitement around metal printing, we see that it's a lot of excitement around part consolidation, around these very high performance structures, very difficult to make geometries, and then a lot having to do with agile manufacturing. And if we kind of break that down, we're looking at really value generation through design and value generation through logistics. And what's exciting is when we look at those kind of three design headings there, that actually overlaps really strongly with the capabilities of modern metal casting techniques. So metal casting is a $35 billion industry. It's widely distributed. Kind of most interestingly, it's a well understood process. It's a mature manufacturing process that produces parts that are certifiable, that are qualified for aerospace and medical use. And it offers a huge portfolio of materials, hundreds of different alloys. So a much wider variety of materials that we can work with than can currently be used with conventional metal additive. And additionally, it also supports custom materials. So you can formulate materials for specific applications. So there are a lot of really interesting things going for casting, including the fact that it can just make incredibly large parts. So really the three technologies that we're talking about combining today are generative design optimization and using 3D printing not as the end part manufacturing process, but really as a enabling technology, critically enabling technology to capture that geometry, and then using metal casting to actually realize that geometry in a material of interest. So with that, I'll hand things over to Andy to give you guys a bit of an overview of our generative design and optimization capabilities.
So we're going to see a bit of generative design. We're going to see basically a piece of software that is currently on tech preview. So the idea behind generative design is quite simple. It's define, generate, and explore. So we start by defining. We look at what we have here is an suspension upright. So we have the green bits, which are our preserved regions. We have the red bits, which are our space claims. And what we do is we set up our structural loads on there, and then we work through our manufacturing constraints, our material options, and basically we then generate quite a lot of solutions from that. So in this case, I've generated 45 designs. So from that, we need to basically work out what are the ones that best meet my needs. So for my application, I'm looking more at stiffness. So I'm looking more towards this lower end here of all these designs. So we've got weight on the bottom and then stiffness on the side. And I can look at those in a bit more detail. So this is a little closer look at one of the designs. So it's got a stress plot on there. You'll notice that the plot is actually very uniform in color. And that shows that it's reaching a very high optimal shape. So this is something that we're using generative design to do within the advanced consulting team. So we're looking at comparisons of materials, manufacturing constraints, we're applying structural loading, we're generating our CAD from that. We can also look at beam and lattice generation. And one of the main benefits of the software is exploration of designs. So here are some parts that I designed from this. So we have 3 different materials here, so we've got 3 different designs. So these solutions, we could additively manufacture those, we could even cast those as well. So here is another suspension upright for a high-performance vehicle. It's looking at the rear of it, looking at the front. And this is a structure used for the handlebars of a BMX bike. This bit in the middle here is actually developed using the Autodesk Monolith software, which is a multi-material generative design software. But the bit on the end in silver, that is what was generated through generative design. It's another image. So here is the same bike, but with the seat frame now. That's the entire bike. And we actually manufactured this. So it's got a composite polymer frame with 2 aluminium structures for the seat and the handlebars. We can use this software to also do architectural designs, so don't think just automotive and aerospace. We can do some very cool things with architecture. So I'm going to move on to lattice optimization, and this is going to focus on the seat frame that we have at the front. So here's a photo if you haven't seen it yet. So the idea behind lattice is basically inspired by nature. So we have an X-ray of a femur bone, and you'll see inside there we have a very porous lattice-like structure, and around the outside we have a varying thickness skin. And this is basically to enable you to have very high stiffness and low density. So the software that does this is NetFab. And in NetFab, we're able to define a lot of different lattice topologies. We can build our own custom topologies in there. And we can manually optimize those here, or we can automatically optimize using our structural loads. And this is all being done through Nastran. So the benefits of lattice structures is you can get thin wall structures, so they're all supported with the lattice. Lattices will limit crack propagation, so if a beam fails, it does not propagate through the entire system. You can get very high second moment of area. So what that means, very high bending stiffness. You can get very lightweight designs. And during the additive manufacturing process, you'll notice that the residual stresses in the part are a lot lower. So you get a lot less deformation. And you can control the structural behavior of the parts. So you can create very interesting features such as negative Poisson ratios, so there's auxetic type structures. But you can control exactly how the structure behaves in certain ways. So I've got a video here. It goes quite quick, but I've got some stills of this afterwards. So what we're doing is we've brought in our parts. We've brought it in as a multi-body component. We're setting up our bits that are solid. We're setting up bits that have got lattice in there. And we're setting up the range that those operate within. So the upper and lower range of the thickness that it's going to operate between. And I'm just setting up the skin thickness now. So you can just see there. So it's just around the outside. So that is the unoptimized structure. So I'm setting up the boundary conditions. So I've set up a symmetrical structure here. So we're imagining 3 seats, 2 seat frames. The loads are on all the bars, so your seat's on the lower bars, the seat back is on the upper 2 bars. And I'm setting up a number of load cases for this. So just to show you a little bit more clearly. So on the left here, we basically work down, developing our range of lattice thickness, and we set up the skin thickness. So you can see here, a little bit more zoomed in. So I can set up the cell size as well, and I can stretch that in any dimension I want. And then we can optimize the thickness of this. And I can also set up the surface thickness. So it just gives you an idea of what happens during the optimization. So it's varying the thickness of the skin and varying the thickness of the lattice. And this is the structural loading setup that I had. So I had a symmetry plane on the far side. So we have 1 seat here. We have effectively half a seat and a symmetry plane. So simulating the 2 frames with the 3 seats. And this is a final part, but you can come and see this one up here. So part of what we do in our team, we also do verification of the models. So we can generate these solutions very, very quickly using Beam and 2D elements. But we want to verify that these are really are the stress that they are actually at. So we do a 3D mesh of this geometry. So you can see here a very highly detailed 3D element model. And we verify the stress. It is a lot lower than the yield. So I'm going to pass you back to Andreas.
All right, so we're going to talk about how we actually made this seat frame, and it's worth noting there are very few metal printers in the world that can fit an object that large. Just quoting it out at someplace like Proto Labs, we would have had to chop it into 4 different pieces and then figure out how to weld together all of those lattice nodes afterwards, which just isn't practical. And likewise, we certainly can't use materials like magnesium in metal printers. So the investment casting process, it's a positive mold process. You basically make a sacrificial copy of your object in a material like wax or plastic. And then you take usually multiple objects, copies of that object, you put it on another piece of wax called a tree, and you build up a ceramic shell, basically build up a temporary mold around those wax patterns. You do that by repeatedly dipping it in a ceramic slurry and then backing that with a sand coat. So you're kind of, it's like kind of a stucco process. You then melt out all the wax, flip the shell over, and pour in metal. So what you've basically done is transferred geometry, a surface impression, from wax to ceramic to metal. Then chop your metal parts off of the tree, heat treat them, machine them, and you have finished metal parts. So we worked with a foundry called Aristocast up in Almont, Michigan. They're a high-performance foundry with a specialty in magnesium. They have a couple of these VX1000 printers on site, and this is what was used to actually print the patterns for the seat frames. If you come down by the booth, the Aristocast and investment casting booth down on the show floor, you can see an example of what those patterns look like. Worth also noting, we're going to be pouring metal on the show floor over the next few days, so definitely swing by to see what this process looks like. The voxeljet printing process here, we're binding PMMA, acrylic powder, together with a binding agent to create that pattern. So we're getting all of the advantages and agility of an additive manufacturing process. We're able to move very quickly and cheaply, as it's always going to be cheaper to print plastic than metal. And we're able to realize kind of the full richness and complexity of the adaptive lattice that Andy engineered here on the seat frame using this technology. There aren't even any support structures. It's worth noting that in addition to the actual seat frame, you can see what's called the rigging, or the metal delivery system, the gating, which are all of those additional features, channels you see. Those basically, once this pattern has been vaporized later in the process, those turn into funnels for routing the liquid metal into the cavity left by the seat frame here. This is the slurry dipping process. It's a color indicating liquid ceramic slurry. So it goes from this kind of green-yellow to an orange, so that you can kind of maximize process efficiency, don't have dry parts sitting. You generally repeat this dip and then sand coat application anywhere from kind of 4 to 12 times to build up a layer between 4 and 20 millimeters thick. You're building up the mold in this process. Once you've built up your molds, you autoclave it, and that melts out the wax so that there's less material combusting during the next stage, which is burnout, where you actually vitrify that ceramic shell to strengthen it and vaporize out any residual material. So it's worth noting there are a lot of different types of materials that can be used for pattern materials, even PLA from desktop 3D printers. We actually did a lot of early work just using $2,000 MakerBots and printing patterns, and we're able to get some very nice parts that way. PLA is basically polymerized cornstarch, burns out very cleanly. Likewise, the PMMA powder that voxeljet uses, in addition to burning out cleanly, has a kind of an interesting effect. It has a negative coefficient of thermal expansion, so it doesn't stress the shell, it doesn't expand as it heats. So it's kind of one of the preferred pattern printing techniques within the foundry industry. After the shell has been burned out, inspected, and cleaned to remove any residual ash, it is then heated up again. And then they first flood the shell with argon, because we're working with magnesium, which is a relatively reactive metal. And you can actually see it flaring a little bit at the top as it comes into contact with some oxygen. It's got an inert gas flux coating in the ladle there. But they're filling up the shell here. Afterwards, once that casting is solidified, it's bead blasted to remove the shell. We have a ceramic shell up here, which you're welcome to come up and take a look at afterwards. It's a relatively fragile material, and after the shell has been poured, it starts to crack. So it's relatively easy to get the shell off using abrasive means like bead blasting. So we're pretty excited about what we're able to achieve here using geometry optimization alone, using the adaptive latticing that Andy did. We were able to reduce the mass of the original seat frame by about 30%. What's really exciting here is we're able to reduce the mass by another, almost 25%, just with the switch from aluminum to magnesium alone. Magnesium has a higher specific strength, a higher strength to weight ratio. So we're able to actually, in the end, reduce the weight of this part by a factor of 2, which is pretty exciting. And so if we take a look at, a seat frame is a relatively small part, but there are hundreds of them on, commercial passenger aircraft. And we take a look at some of the biggest aircraft in the world and some of the biggest fleets in the world. So say looking at Airbus A380s, which have a little over 600 seats on them and kind of maximum passenger capacity, we end up saving a little over $200 million over the lifetime of a fleet of, say, 100 aircraft, which is pretty exciting. Looking at the costs, this was one of the things that's pretty exciting. Casting's pretty cheap. This is about 3 times cheaper than, just in terms of looking at laser time, about 3 times cheaper than a conventional metal printing process. So at prototype quantities, we're looking at about $4,000 per seat frame. And when you start to kind of run the numbers on making larger quantities of these, what's interesting is you can pack these volumetrically, which is another thing that you can't do, kind of an economy of scale that you can't achieve with metal printing, where you don't really do much 3D packing. You can actually pack up to 80 patterns, 80 of these seat frames into those VX1000 build chambers. Take about 72 hours to print the entire chamber, but you're averaging a little under 1 hour per pattern. So we're actually moving through this process pretty quickly. Additionally, there are a lot of, the kind of general impression in the industry is that casting is a very slow process, and that's only slow when you're cutting tooling. It's actually extremely fast. You can go from printed pattern to part in about 8 hours using some of the modern high-speed investment casting shelling techniques. So there are certainly a lot of interesting characteristics of the sand industry, a lot of the casting industry, excuse me. There are a lot of kind of misconceptions around the kind of the turnarounds and lead times that are largely holdovers from using conventional subtractive processes, which are really the rate-limiting step when you're making tooling for, say, molds for wax parts or tooling for sand molds, which we'll talk about in a minute. That being said, typically you're quoted about 3-4 weeks for investment cast parts, but oftentimes if you pay an extra 15-20%, you can get up to turnaround times as low as 2 days. So it's pretty exciting. We also ran some of the castings that we did through a CT scanner and X-ray just to check for some of the kind of traditional casting defects. So what we're looking for here is porosity, which can manifest at a couple of different scales, but we're excited to see that there's no visible porosity using existing conventional inspection techniques. So we're pretty excited about that. In terms of actually designing for this process, this is a little bit different than designing for, say, a direct metal additive process. But what's important is that you have to design for the entire process, for everything that's going to occur between CAD and finished parts. The joke in the casting industry is that people don't buy castings, people buy parts, and a lot has to happen to a casting to get it to be a useful part. So in addition to designing for your functional requirements during service, you also have to design the parts with shell buildup in consideration, shell removal, design for the actual casting process, as well as consider heat treatment and machining steps. So again, the shell buildup consists of that slurry dip and then that sand coat to build up that complete layer. We generally go through between 4 and a dozen layers. And what you want to think about here is we've got kind of 2 mechanisms here. We've got a fluid flow challenge of getting getting that liquid ceramic slurry to coat every surface evenly to correctly build up that mold wall. It's important to think about, what we're doing here is we're constructing that mold. So we're building up the mold. So you want both components of the sand and the slurry coat to have access to that part. So you can see what a shell built up around a wax pattern looks like up top there, and then what the finished casting looks like. So with these turbo snails here, there's generally a bit of rotation during the dip process to make sure that you get that even coat. Another thing to consider is, you're making the parts that you're making, the pattern has to survive the shell buildup process without deformation. So the structure that you're making has to, in addition to being stiff enough to satisfy the requirements of its service life, also has to satisfy the process, or has to withstand the process of being submerged into that ceramic slurry, being rotated, being handled when it's realized in a much more delicate material. These printed PMMA patterns, they're kind of the consistency of a sugar cube, a little bit lighter, so you can definitely kind of scratch and abrade material away with a thumbnail. And it's relatively brittle, so very, very fine, thin features will break. So that's something to definitely keep in mind. Probably one of the most interesting and important things we learned exploring these lattice geometries is around negative features, so cavities in your geometry. As a shell is built up, this is just a part of a kind of three-dimensional lattice geometry here. You can actually see the 9 individual layers of that shell, of the ceramic slurry, and then the back coat of stucco here. And what's important is to make sure that all of those negative features are at least twice your shell thickness, so that you can build up a complete shell. Because otherwise you're going to essentially end up with a defect in your mold. What that looks like, and you can actually see this part afterwards when we go to questions. If you don't build up a shell of correct thickness, you're going to get a fracture, and metal is going to leak into that kind of inadvertent mold cavity. And so what you end up with are these weird little nuggets of metal trapped in a lattice geometry like this. So this is one of the early seat frame prototypes where we didn't have those negative features properly sized, and so we got defective shell formation in those cavities. And got these little nuggets of metal in there. So we did a test piece here, a couple of these test pieces, to come up with some kind of basic design rules. We generally found once you have cavities above 13 millimeters, you have plenty of access. But we were doing a body-centered cubic lattice cell here, 20 millimeter unit cell. Once we had struts below 2 millimeters, we started seeing those struts breaking during the pattern portion of the process. And likewise, when we went to higher relative densities, so on the far right there, struts of greater than 8 millimeters, we started getting below that twice the shell thickness criteria, so less than 8 millimeters cavity size. We started getting incomplete shell buildup there and getting defects. Another important aspect, designing for deshelling. This is a lattice cube that still looks like this under my desk, because after an hour and a half in the sandblaster, we're not able to get the shell out of that. So you want to think about how you're going to get the shell out of your parts. You want to think about lines of sight, because you're going to be using generally kind of high velocity abrasive media or water jets to get it out. So you want to make sure that you can see every piece of the shell that you want to abrade. That being said, there are some kind of exceptions to the rule. You can also pay a lot of money and have your part thrown in a bath of molten salt that will actually dissolve the ceramic, but that adds quite a bit of lead time and cost. So generally we found sticking to 1 or 2 layers of unit cells is a pretty good rule of thumb, and also abiding by those negative feature and positive feature rules to make sure that your positive features are going to withstand the whole process, and that your negative features allow for full shell buildup. Additionally, the casting process itself comes with a lot of its own design constraints. We're working with a process that involves a phase change, so there's a densification that happens, and there's a lot of considerations around fluid flow and heat exchange. So thin features are gonna cool more quickly than thicker features. And you likewise also want to minimize the turbulence as that metal flows into that cavity, because metal has momentum, and that momentum is going to be transferred to the structure of the mold. We're working with a relatively fragile mold here, so you want to keep that in mind. And you also want to maximize the speed with which you fill that cavity. So there are a lot of considerations, and generally it's best to work closely with your partner foundry to really kind of talk through the details of the casting process to best kind of understand how that affects the design of your part. Finally, as with kind of most near-net shape processes, we're designing for generally with the some sort of post-processing in mind, generally heat treating and machining. So you definitely want to think about whether you need to add fixturing features, any kind of tie bars or anything. If you have features that are quite distal to each other, that are high tolerance, you might want to add a tie bar so during heat treatment those don't wander too far away. So another thing to consider in terms of full process planning. So next we're going to take a look at another project, switching gears to sand casting. This is working with an outfit called Lightning Motorcycles. They're based in San Carlos, make a 200 horsepower electric motorcycle that is the fastest motorcycle in the world. Has some really interesting characteristics due to the fact that it's an electric motorcycle, and we can talk about some of the kind of momentum physics afterwards. It's pretty neat. We decided to take a look at the swing arm on this because it's working with a high performance application here. Currently it's 3 pieces of billet CNC 6061 bolted together, composing that swing arm. Weighs just under 7.5 kilograms, and what Lightning wanted out of this collaboration was to maintain part performance while reducing weight. So what we did is, let me go ahead and play the video here. Now is the video playing? There we go. So we loaded the bike up into Fusion, isolated the swing arm, and then extracted the geometry that we used to actually run the generative design synthesis here. So we basically have the bearing races for the motor mounts, the suspension tie-ins, the axle mounts, go through, select the materials and manufacturing processes we'd like to explore, and then we generate that huge variety of options here, basically doing that matrix of manufacturing process and material. And then we can go and interrogate all of those different options, those hundreds of different options. We can look at deflection, we can look at von Mises stress, and we can really look at all of those compared to our one of our most important criteria here, the weight. So let's go ahead and take a closer look at kind of what that generation process looks like here. Just exploring a bunch of the different options using different materials, what that synthesis process looks like. And then we took those results, threw them back into Fusion to do the actual validation studies. So you can actually go see this bike. It's down on the show floor, and you can also see the sand molds that was used to make that swing arm. We're pretty happy ultimately with the performance. We're able to match to within about 15% performance on all of the primary load cases, except you can see for the middle one a big deviation, but that's actually because we're 50% stiffer. So in this particular load case, this means that the acceleration that you get as the electric motor kicks in and yanks the chain, applying a kind of a vertical torsion to the swing arm, the swing arm deforms significantly less. So we're pretty excited about that. It's worth noting that this is actually a pretty high precision manufacturing process. This part is about 700 millimeters long, and we're looking at most just shy of a millimeter deflection in these white light scanning results. This is after heat treatment. Additionally, we did a full CT scan. We're just looking at 4 different sections. It's a little hard to see what we're working with here, but you can see that these are all nice, even. There's no holes in these white solid regions here. So we've got a nice sound casting as a result of this. So again, this geometry was made using 3D printing to kind of augment the casting process. Using voxel jets, this is actually one of the largest 3D printers in the world. They're printing sand, so they're using that same powder and binder process, but instead of printing a plastic, a sacrificial material, we're printing a material that will actually withstand the heat and temperature of the sand. These are 2 different kind of mold configurations here. There's kind of the sandwich flavor of mold, in which you basically take a big volume of sand, Boolean out your part, and then just add some slices and alignment features so that you can actually assemble this. So you can see this very sand mold downstairs. And then for the hack rod, which we have up here, we used more of a traditional mold making process in which you actually have a 2-part mold with a core structure. So we're really defining all of the surfaces, external and internal, using that approach. To show you in a bit more detail, this is what kind of a typical sand mold, specifically the sand mold that we used for this hack rod looks like. This is actually the mold for the big brother of this one, which weighs 40 pounds. This one weighs 11 pounds, so we took it, it's a little easier to carry. So you can see that they're using an overhead crane. This sand is actually it's not lightweight, so it's definitely a consideration when designing these molds. So they're assembling the mold here. You can see that core inside the primary mold. You can see holes here for load straps to actually move these pieces of mold around. And you can also see that there's a little bit of kind of metadata information embedded into those mold components. So there's a lot of opportunity to ensure that you're pouring the right alloy, assembling the right molds, working with the right version of the geometry, which is quite nice. And this is the raw casting. This is after it's had its gating and risering chopped off, but you can see those gating scars there. Those will be ground down, and then you can also see a little bit of flashing around the outside. But this is just a matter of a few hours with some hand tools to bring that down. Here's what the finished castings look like. You can see the big one on the right and the little one down here. So again, the idea here is you have to design for the entire process. This is a tour through the facility where this was made, and they have both heat treating, machining, and inspection services in-house. They actually have probably almost 60 multi-axis machining centers there. So you want to design for your 3D printed sand mold. You want to keep in mind that you're working with a somewhat brittle, very dense, heavy material. And you want to design again for those casting rules, design for heat treatment, design for machining, and then also keep in mind inspection. That first version of the hack rod we made didn't actually fit in their CT scanner, so we don't know what's inside it. So something to keep in mind. So working with printed sand, again, it's really heavy stuff. You want to make sure that your molds have alignment features and that you're kind of, again, designing in mind. You're basically making synthetic sandstone here. So you want to make sure that you're not doing extremely fine features. We'll talk a little bit about feature scale in a minute. Additionally, you basically need to gain access to every surface in the mold. To make sure that that's been properly cleaned. There's basically, after the printing process, there's just a little bit of free loose sand stuck to those internal surfaces. So you just need to get in there with a brush and remove that sand. So you can see that being done here. Often sand molds are shipped with all that extra sand in as a bit of a packing material. So again, solidification, it's this heat transfer process. It's the process of that material transitioning from a liquid to a solid. Generally, you'll work with your foundry to kind of develop, kind of optimize your design to interface with their gating system. But we can take a look at what solidification looks like for the actual swing arm here. So you can see, in addition to the parts solidifying here, you can also see that they've added some material for the post-machining steps that we're going to do. So particularly down in those wheel mounts there, those are the last areas, those thickest areas, the last ones to solidify. So for the post machining, we had to think about both machine access and also add stock to all of those precision surfaces that we're going to machine down, and also think about fixturing and work holding. One of the kind of easiest ways to do that is just to throw some tabs that you can grind down afterwards. Throw those on some convenient locations. Another way to do that is actually to add some kind of subtle flats that you can pick up with a bed of posts at known height, and you can make some fixtures. That might be a better approach if you're going to be doing a more of a production run. So in terms of feature size, kind of scale that you can work with sand molds. One of the things that's interesting, so unlike what we were talking about with investment casting, inability to access kind of long, tortuous channels, being constrained by the fact that you're building up that mold structure using fluid flow, because we're actually able to print every surface here, you can make these long, tortuous passages. So you see a lot of kind of integrated hydraulic lines, coolant lines, a lot of kind of highly multifunctionalized geometry as a result of this. So you can see some free-floating kind of channels or core structures there that will ultimately define fluid flow channels in this casting. Typically with sand, your kind of safe space is working with both positive and negative features of 3 millimeters. You can certainly go down finer, but that's starting to kind of toe the edge what's possible with this kind of synthetic sandstone. One of the most exciting things, though, is that these sand molds are basically like giant Legos. It's only 13 cents a cubic inch, so you can estimate the cost pretty quickly. But you can print, design these mold components with as many alignment features as is necessary to tile them together to make very large sand molds. So at that point, they're really the only limiting factor in how big the parts are that you can make is how big a ladle, how big a kind of pot of molten metal you have. And some foundries are set up to actually pour from multiple ladles. So Tooling and Equipment International, the foundry that we worked with for the hack rod and the seat frame, or sorry, the hack rod and the swing arm, they can do about 2,400 pounds of aluminum in a single shot from two 1,200-pound ladles. So you're starting to work with some pretty big geometries, which is pretty exciting. So just some takeaways. This is the big brother of the little part that we've got up front. What we see here is that many of the same value propositions that have really been driving the conversation around metal additive are in fact possible with conventional metal casting techniques when we really define geometry using generative optimization and then use additive to actually kind of make the mold components here. So it's important to remember that kind of unlike direct metal techniques where we're still trying to figure out the long-term and fatigue properties, all of that qualification work has been done, has been performed for casting processes, so it's possible to very quickly make a qualified part using these technologies. There's a huge portfolio of materials, and you can go extremely large. So with that, we'll go ahead and break for questions and start passing around some parts. Thanks. I'll start passing this guy around. Yeah. Yeah, so great question. Question from the front. Are the sand molds reusable? Both the investment casting and the printed sands processes you've been talking about, these are sacrificial mold processes. So you do need to make a new copy of that mold every time. However, that's kind of fundamentally what lets us make these unmoldable geometries. Oh, I'm just going to grab this one. This one's really fragile, so I was going to hang on to this. Yeah, definitely come see this afterwards.
During the design process, how do you account for shrinkage of materials during the casting process?
Yeah, so definitely you can talk with your foundry to get an understanding of what those shrinkage factors are going to be. Typically, the foundry will apply that factor. If it's something that's going to be very critical to your particular application, generally having just a back and forth dialogue with them will let you address that. We're looking often between 1% and 2% for aluminum alloys. Other alloys have, different shrinkage factors.
How much are you pushing the industry to go towards this method of make, like you're talking about printers not being large enough or something like that, or CT scanners, like how much are you pushing the industry to go in this direction?
Yeah, so the question is how much are we pushing the industry to engage on this, go in these directions? It's interesting. The foundry industry itself has been contracting for probably the past 50 years or so. It was a hard industry to get into. I used to, as I call up these foundries and introduce myself as a researcher, some of them would just hang up on me. There are definitely a lot of crusty old folks really like set in their ways. However, that being said, there are also some tremendously forward-thinking folks out there, both TEI and Aristocast. If you guys want to get in touch, by the way, these are websites, emails. These guys are really leaders in their field. I mean, Aristocast had a 3D system, like the 5th 3D systems machine. So actually, these were some of the earliest, casting was some of the earliest applications of this technology, of additive technology for pattern making. However, it was only ever the kind of agility value proposition in terms of being able to skip hard tooling and just go to prototype patterns. Nobody's ever really driven the geometry side of this discussion. So these are some of the first kind of big latticed parts to be made. Certainly there are other folks beginning to explore these kind of more topology optimized, shape optimized forms. But yeah, the foundry industry is a very fragmented place. So it's hard to make some generalizations about it. But generally, I think the more people start throwing these, exotic-looking geometries at foundries, the more they'll realize that there's a really interesting opportunity to capitalize on this.
Can I add to that? I think it's just a weird time that we're in right now because manufacturing leaving the U.S. So a lot of these companies that you're talking about are opening up their doors to more job shop type work. For many years, I too got hung up on over and over. But now we're finding our way into these doors to large manufacturers that have these dinosaur machines sitting around that aren't getting used anymore. So that they're definitely open to a lot of new ideas. I would say get out there and help everybody try to open all these doors because it's been a real struggle for us as fabricators on our end, try to get into doors.
Yeah. In the back.
What tools do we need to do generative design? Is that in Inventor or do we need an additional Autodesk tool?
So that's in Autodesk Generative Design. It's a standalone tool at the moment. And the latticing was done in NetFab, which is also a standalone tool.
Do they have plans in
Sorry? Yeah, so Generative Design is currently in tech preview, but NetFab is available.
Are they going to make plans to make that an add-in for that?
Sorry, say that one more time.
Are they going to make plans to make that program an add-in into that?
So we're trying to figure out where that technology is going to manifest itself. If you're interested in the tech preview, we can put up an email address that you guys request access to.
Yeah, that was my next question. Can we get access to this information as well?
Yeah, and so the presentations will be posted. Sorry.
Yeah, that's why you're here.
We'll put up an email address here in a second, and then you can request access and we'll see where it goes.
Yeah, so we're already using Generative Design seamlessly with Inventor and Fusion, so it works extremely well already.
So I was kind of thinking that maybe in the interim you can make that accessible through the wall.
Was that through Vault?
Through the wall.
Potentially.
Accessible to the wall where you could tag it through Inventor for now. You understand what I'm saying? So you piggyback it through the wall.
Right. Yeah, I think we're, as Doug said, Doug, by the way, is product manager for our generative product. Yeah, we're still exploring kind of how exactly this is going to manifest, but currently it's a standalone.
When you say tech preview,
Yeah.
Well, I'll tell you why I'm interested in this. The molding that we do is actually unique. We mold epoxy.
Okay.
And it's a very lengthy process in doing that because it has to be under compression and slowly heating. And when you're talking about making anywhere from 500 to 600 insulators, taking 8 hours to produce one, kind of hurts your lead time on being able to get things into production. You can't build boxes until you have insulators. Insulators on average about 8 hours a piece. So if we could increase that speed, that would be very good.
Okay. Yeah, let's follow up after that afterwards.
Yep.
Other questions over there?
So what's stopping this from scaling? What are the hurdles between now and Airbus, Boeing throwing these types of seats on aircraft?
Yeah, I'd say it's largely with a lot of these new technologies, it's more of a social engineering problem than a technical problem. There's certainly, I mean, these are pretty exotic looking forms. It's, particularly with the swing arm, challenges a lot of traditional design intuition. So I think that there's just more demonstration work has to be done. Andy, you spent quite a bit of time at Lockheed Martin, so maybe you'd like to comment on aerospace.
And we're working with customers like Airbus and those guys, and you'll have seen some of the work that we've done with generative design before with the aircraft partition. Those guys are at a very high level at the moment in their technology readiness level with additive. This is an easy way for them just to take it slightly higher and basically scale up their production as well. So there's definitely a lot of interest from the aerospace industry in this technology.
Question over here.
Kind of piggyback off that, how much are you, I mean, I guess this project is a little bit on your own with a company that kind of agreed, like what on the side of like aesthetics versus truly engineering, because this is almost like letting engineering do the design work, like how much of the aesthetics goes back into it?
Yeah, I've certainly got a comment on that. I don't know if you wanted to.
So yeah, so what it's giving you is a very, very sort of computerized view of what is the optimized geometry. It is very easy to actually manipulate those geometries afterwards. We can do that in Fusion on the T-splines. We can do that in some of the other software tools like 3ds Max, Mudbox, things like that. And we do that. So you'll have seen probably the first set of 3 uprights. That's something that we did to that. We basically reimagined the same design.
Yeah, so I think that, you know, a lot of the aesthetics of these kind of mathematically optimized forms they do kind of tap an interest in their kind of, you know, their biological nature.
Yeah.
However, as you know, computation continues to drop in cost, the cost to develop those is also going to drop, and I think that ultimately, I think we're looking at a kind of a bakelite aesthetic, and that I think it's going to become pretty rapidly commoditized over the next 5 to 10 years as an aesthetic that is less associated with high performance parts and more associated with low value parts that aren't that we spend less human engineering time on. So the question is about inspection, and yes, we compare CT scan data for dimensional distortion as well as internal void. So it's typically CT and X-ray for determining whether or not there are any voids, and depending on the application, for instance, for medical, after the part has been CT scanned, it's then 3D machined, say for custom knee implants, and then subjected to a dye penetrant test. To look for any sort of microcracks, fissures, things like that. But what's great is there are existing, totally well understood qualification protocols for this. Yeah. Other questions?
Has this been running on the electric bike for a decent amount of time?
Yeah, no, we just installed the bike. Question is, have we run the electric bike with the new swing arm? We have not yet run the bike. In order to hustle to get a part here for AU, we cast it in a lower strength but more predictable alloy A356. We're looking at the 200 series alloys, which will bring up those mechanical properties here. So we cast it in, these are the specific strength chart, cast it in A356, which you can see, not great properties. These are the alloys that we want to cast in. So these are the 200 series aluminum alloys with really high yield strengths, around 400, 450 megapascals. So we're looking similar to things like APWorks Scalmalloy, which is what we printed the bionic partition in a couple of years ago. All right. Any other questions? Just remind everybody that we'll be doing some live casting demos downstairs. So we're going to be melting metal in the microwave. Turns out that's a thing that you can do. It's pretty great. And we'll be just casting small medallions using the investment casting process out of tin. So definitely recommend if you guys want to learn some more about that, see some printed patterns, come swing by the booth down there. And also definitely swing by, take a look at the motorcycle swing arm. We also have the actual sand mold there, so you can take a look at that, get a sense of the scale. It's composed of 4 75-pound chunks, 300-pound mold total. So you can get a sense of kind of what the scale and the kind of capabilities of the process are there.
That tech preview for the generative design technology is actually at the idea exchange. So if you want to go try it, just stop by the idea exchange, David, here's the link, and you can get your hands on it.
Great. All right. Well, thanks, everybody. I just asked that all the parts come back.